Me from Birmingham.
Okay, hello everyone, and thank you very much for the introduction. So I want to talk about solving unconstrained binary quadratic optimization problem by Lasserre hierarchy and unconstrained point method, which is a collaboration of myself, my supervisor Michael Vectorizing, and Michael Stinger. And before I start, just need to mention that this is just part of my research during my PhD, and it's not the complete one. So. In the first slide, I would like to bring a brief outline that about what I will talk today about today. So, our purpose, our goal is to solve a non-complex binary quadratic problem. And so to do so, we use a Lasserre hierarchy of relaxation technique. And also, I will discuss the dimension of the relaxation. And to solve this relaxed BQP, we want to use our code, which is called Lorraine. And so I will introduce Lorraine and also some assumptions that under this assumption, Lorraine will be efficient. And after that, I will just explain about the interior point method and the Lorraine preconditioner used in Lorraine. And after that, I will bring some reformulation to this relaxed BQP. And the reason is that there are some assumptions with Lorraine, and we need to make the relaxed BQP in a way that it fits Lorraine's assumption. And finally, I will bring our numerical result, which will show the efficiency of our method and approach. So let's start. So here, I just brought the notation of the linear semi-definite optimization that we are solving. And here's our primal STP, because some people might know it as a dual STP. And n is the size of matrices, and n is the number of the equation. And also here is the Lagrangian dual for this STP. And here it is. So now I would like to talk about unconstrained binary quadratic problems. As I mentioned in the outline, our main purpose is to find the global minimum of non-convex binary problem. So here we minimize a quadratic function over a constraint that the variable xi would be in a set B, which this set B is binary, or it's either 0 and 1 or -1 and 1. And also the matrix Q here, the real symmetric matrix Q is of the size S. And we do not have any sparsity in Q, and it is generally a dense matrix. And the technique that we're using here is the hierarchy of convex conic relaxation. Kim and Kojima in their paper in 2017 also studied these BQP instances, and they identify these BQP problems as a challenging problem for developing conic relaxation methods. So we are also saying that these are challenging problems for developing a new STP software. So here, as I mentioned in the last slide, to find the global optimum, we are using Lasserre hierarchy of semi-definite optimization problem, relaxation of growing dimension. And so the STP relaxation of the BQP problem that I showed in the last slide is in this form, which in here, the matrix M is a moments matrix, which is a dense matrix from a very specific form. Also, for the order of the relaxation 1, this Q here would be equal to the spec of the matrix Q, which is the vectorization of the matrix. And in particular, if the solution of the BQP is unique and the order of the relaxation is high enough, the rank of M, the rank of M moment matrix would be equal to 1. So now I would like to talk about the dimension of the relaxation. So the size of the BQP will change by the order of the relaxation, and it's completely dependent on the order of the relaxation, and it grows very fast by that. And it will the size of the matrix will follow this term, which in here omega is the order of the relaxation, and f is the dimension of the BQP. And also as the order of the relaxation goes high, the number of the variable also goes high. But we do not have any specific formulation for this number of the variable. But just we know that this lower one that we have here is just the estimation of the number of the variables based on our numerical experiments. And also this number of variables goes high by the order of the relaxation till it reaches the saturation point, which is to the S minus 1. Here, I brought a little table to show some examples for this growing dimension. So here, for example, for the BQP of the size S equal to 9, for the dimension set 9, for the order of the relaxation 2 to 5, we can see that the number of variables also grows from 255 to 511. And the matrix set also grows from 45 to 381. So we can see that it's growing. There is a theorem which is predicted by Lorentz and then proven by Fuzzy that one has to go up to half of the S, half of the BQP side steps in hierarchy to reach the exact solution. So, and this is proved by some examples, but we can see that by this approach, even the moderate size BQPs wouldn't be able to solve by this approach. For example, in this table here, we can see that for the BQP of the size S 21, 35, 41, and 51, we can see that the relaxation it went up to the half of the S. It is 11 to 26, but we can see that how the matrix size is growing. Even in the level of the S21 is big enough, and it's growing from 784,000 to 10 to the 14. So we can see that for this problem with the S bigger than 20, it seems that it's unsolvable by this approach. So far, what did I say? I talked about the relaxed BQP and the dimension. And we said that we do not have any sparsity assumption on the BQP. So we cannot use any sparse techniques which is available. So we are proposing to use our recently developed code, which is called Lorentz. And in this aspect, I would like to explain more about Lorentz. That's what it's doing. So Lorentz, it comes from Lorentz interior points method, and it uses a primal dual predictor corrector interior point method together with iterative solution of the resulting linear system. And this iterative solver is a precondition Krylov type method with a preconditioner utilizing a low rank of the solution. And Lorentz implemented in MATLAB and Julia, and it is proved to be very efficient for STP problems with very low rank solution. But this efficiency happens under some assumptions that I will tell in the next few slides. So before I will talk about the Lorentz assumptions, we have a look again to our primal STP and the dual STP. The first assumption in Lorentz is that the solution of the primal STP ESR has a very low rank, and actually we developed the preconditioner based on this assumption. And the further assumptions are that we have a flat condition and a strict complementarity. And also we have a sparsity assumptions that if we let's define the matrix A to be a matrix which its columns are the vectorized form of our data matrices A1 to AN. So in this sparsity assumption, we assume that the matrix vector product with A and A transpose may each be applied in OM blocks and memory. Also, we have the sparsity of B, which is in our linear term, and it is that the inverse of B transpose B and the matrix vector product with this inverse may each be computed in OM blocks and memory. So I told you about Lorentz. Now I want to get a little bit far and talk about the interior point method and the preconditioner that we use in this Lorentz. I will talk about this here. And before I start, I want to let you know that the whole process to the preconditioner is just by considering the STP problem without the linear constraints, because of it's simple, more simple to explain it this way. And yes, so I will start, and this part we finish with the preconditioner that we want. So in each iteration of the interior point method, we have to solve two systems of linear equations in the variable y, the predictor and the corrector. And this linear system is, as you can see here, this page yi is our linear system, and in here, AI and AJ is our data matrices, and W, the matrix W here, is the scaling matrix that I will talk about it in the next few slides. I will show you. So vectorizing the matrix variable allows the lab system to be compactly written as this system. This is our short complement equation, and this is our main equation that we would like to solve with its special properties. And we can see that here the matrix D there is a Kronecker product of W and W, and W is our scaling matrix that we just said. Now we want to solve this short complement equation. One of the ways to solve this short complement equation is by using conjugate gradient method, which is an iterative method. But there are some problems happen in assembling this H, the short complement matrix, which is that H is large and sparse, and so assembling it might be expensive. And another problem, and more importantly, is that H becomes increasing ill condition as the outer interior point method makes progress towards solution. A successful CG-based solution of the equation would be rely on an efficient preconditioner. So instead of conjugate gradient, we will use preconditioned conjugate gradient, which we call it PCG. And in PCG, we do not need to assemble H anymore, which was the difficulty for using conjugate gradient. And we only have to compute the matrix vector for the H set, which you can see here, and is the left-hand side of the system that I showed at the beginning. So now I would like to talk about the scaling matrix that I mentioned, and also the ill conditioning, which is happening by the scaling matrix. So the positive definite symmetric matrix W is our scaling matrix, and it captures the curvature of the log-depth penalty function in the which is happening in the interior point method. And there are three ways to construct this W: is primal scaling, dual scaling, and Nestor plot scaling. And actually, we're using this Nestor plot scaling. And in here, if we consider our current iterate to be the set of x hat, y hat, and s hat, the W coming from Nestor plot would be the unique positive definite matrix satisfying in this term, which is this equality, which is x hat equal to W s hat W. But there is a point that in all these three cases, W, no matter which one we use, W becomes increasingly ill-conditioned, as much as the interior point method getting closer to the solution. And actually, this is the mechanism which causes the ill-conditioning, and we will try to solve this. So now I would like to tell you about the preconditioning of this short complement matrix. So there is a critical observation by Zhang and Lasserre that if the solution XSR, the solution of the primal state, is low rank, then W, the scaling matrix, is low rank. So we are using this low rank property here, and the idea of the preconditioner comes from decomposing W according to this its expected rank. So, for example, if we consider that the solution XSR has rank K, then the scaling matrix rank tends to be also K. So we decompose this W in this way, by considering K to be the rank, the matrix U there would be a full rank matrix, and this lambda S here is a diagonal matrix, which is including the n minus K, the smallest eigenvalues of W, and lambda L would include the K largest eigenvalues. And also that tool there is chosen in a way to satisfy this inequality, or more exactly in what we're doing, it is proportional to the average of the eigenvalues of W0. So now we replace this decomposed W in the short complement matrix that we have here. And we get this new short complement region. And now we approximate this W0 here by tau times identity, and it gives us the H tilde preconditioner. And H tilde preconditioner is a preconditioner by Zhang and Lasserre. And by using Sherman-Morrison-Woodbury formula, the H tilde inverse times Z would be written as. So now we have we got the H tilde preconditioner from Zhang and Lasserre, And by replacing the term A transpose A by identity matrix, we want to introduce a new preconditioner, and we offer the new improvement on it. So the new preconditioner, we call it H alpha preconditioner, which is the square of tau times identity plus Lilly transpose. And there are several advantages of H alpha compared to H tilde, and which is it is cheaper to compute and apply compared to H tilde, and it requires less memory, and it is more efficient, and not only it works for low rank problems, it also works for almost low rank problems. So at the beginning of the interview points method, I told you that I didn't consider the linear constraints in the STP, but here is the general form of the preconditioner for the general problem with P-linear matrix inequalities and a linear constraint, dy greater than or equal to P. And so here is H alpha precondition for the general form. So in this figure, I want to show you that why H alpha is good preconditional. So in this figure, here, you can see the distribution of eigenvalues of the show complement matrix. And you can see that the eigenvalue, there is just one distinct eigenvalue, and the rest are spread from, it's not 0, it's more than 0, around 50, to around 3 times 10 to the 8th. But in the right hand side, you can see the distribution of the eigenvalues of H alpha inverse H, which is the precondition matrix. And you can see that most of the eigenvalues are equal to 1, and the rest wouldn't exceed 1.36. So, which shows that this precondition matrix, has clustered eigenvalues, and the condition number is very small. So we can see that why H alpha can be a good precondition. So, so far I showed you the BQP problems and the relaxed BQP, and also I introduced the code Lorraine that we want to solve these BQP problems. What's the relationship between Lorraine and this relaxed BQP? To be able to use solve this BQP, we need to relax BQP. We need to have the assumptions of Lorraine also satisfied for them. So we check the assumptions. The first assumption for Lorraine was that the solution of the primal STP X star has a very low rank. But the STP relaxation of the BQP, the relaxed BQP, has the form of this dual STP with a low rank solution in S. And it's exactly in the opposite of what we want, for the low rank. So by using some additional variables and equality constraints, we will reformulate reformulate the relaxed BQP as in the form of the primal STP with the low rank solution X.
Ask a question?
Yeah.
Just so I can order my thoughts. What is the difference between very low rank, almost low rank, and full rank? I know.
Yeah, it's very low rank. So the low rank problem, it has a low rank problem, but if I'm not trying for almost low rank problem, we add amounts to the problem to make it low rank. Yeah, do you have some examples for it?
Can you explain to me low rank in terms of a percentage of full rank, something like that?
What do you mean? Can you give me an example?
So what does low rank mean? Like, is 1,000 the low rank if you have a million by million matrix, right? What do you mean?
I think it's very, yeah, very.
1 or 2. That's,
yeah, exactly.
That's very low. And low
Yeah.
rank is what, up to 5? Okay. Up to 5.
Yeah. It's really question. For large. Yeah. So let's see. Not 1,000. So here. So we said that we have this relaxed BQP here. So we want to rewrite this relaxed BQP in a way that it fits the Lorentz assumption, and we would have we would write it in a form of our primal STP. So the dual problem to this BQP relaxed BQP can be written as this problem, which is BQP relaxed dual. And in here, the matrix M is the matrix, which is both are the vectors form of the matrix M1 through Mn. And the size of the number of the variables here is the half of the square M plus M, which is equal to the size of M. So here is the PQP real dual. So now the dual solution to this PQP real dual has rank 1, and it's exactly in the way that Lorraine can solve it. So we have this PQP real dual problem, but we said that in Lorraine we are using interior point method approach, right? And we know that interior point method technique is designed in a way to solve problems with inequalities, and it cannot handle equality constraints, especially many linear equality constraints. So to fix these problems, there are different ways to do that. You know, the simple way, not the simple, one of the way is just writing this equality to inequalities, but the one that we're using here is by using the L1 penalty approach. So by L1 penalty, so here we just add the known one of this equality constraint to the objective function with the mu, which in here mu is the positive mu is the penalty parameter, and we get this problem. And now I introduce two new non-negative variables R and S. We write this mz minus q tilde as R minus X. And by using the identity, this identity, we eliminate the variable R, and we get to this final problem. So this, and here is our final problem that we want to solve, and we can see that we just have inequalities, and it's in a way that Lorraine can solve it. So let's see. So we talked about Lorraine and its assumptions, right? So we first fix the first assumption by writing the dual, but there are also some other assumptions that it needs to satisfy for the BQP relaxed final problem. One of the assumptions were the sparsity assumption for Lorraine, which was that for this matrix A, the matrix vector product with A and A transpose may it be applied in ON flux and memory. So the same thing happens for the BQP relaxed real final problem, that we had this LMI, the snap of Z was positive symmetry. So we can write this as snap of Z as a summation of AI ZI. So we are going back to our notation for the Lorraine that we have for Lorraine. So by considering this as a snap Z, every matrix AI contains at most 2 non-zero elements. So it is trivially satisfied. So we have another sparsity for the B, which was in our linear term. And the sparsity was saying that the inverse of B transpose D and the matrix vector product with this inverse may each be computed in flux and memory. And this assumption also satisfied for this BQP real final problem. And we have this lemma to show that, which is one of the properties of the Lasserre relaxations. And that there exists so if this, so D in the BQP relaxed final was M here. So just in case it is M transpose L is not a block diagonal matrix. So there is a permutation matrix P such that Tn transpose NP transpose is block diagonal matrix with a small group blocks. And in particular, M transpose M is a sparse core dot matrix. So, okay, so now I want to move to the numerical experiments. So for the numerical experiments, we are solving the BQP problems, which are randomly generated. And in this BQP, we consider the variable xi to be in the set of -1 and 1. And this Q, the matrices Q are a full rank indefinite matrices, which are generated by this code. Or if I want to make it simple, to see that this Q is equal to this, which in here this Q is randomly generated. And also we have an observation that for the Q constructed with this MATLAB code, the relaxation order 2 is sufficient to reach the exact solution of the BQP.
What?
It's just based on the numerical experiments. You know, it doesn't. It's just an observation for these problems.
Okay, so we're saying generic.
No, it doesn't happen for everything. It just yes. So if we just get the Q by using this MATLAB code, we get that. Yeah, it doesn't. There are some examples which shows that it doesn't happen. It's not a general, you know, observation. Sorry? Yes, yes, exactly. Thank you. So by using this, if we generate our problems with the MATLAB code that I showed before, we have these problems of great dimension from the VQ side 10 to 50. And also we use for this problem, we want to use the relaxation order 2 because of that observation that we have. And here I just brought the table to show you the size of our problem. And you can see that for the VQP side, problem 10 to 50, for the VQP real problem, the relaxed VQP, the original relaxed VQP, the number of the variables is going up to 251,000, and here is the matrix side. And this relaxed VQP is the matrix, is a problem that because we want to compare our result with MOSEC, and this table is the one that MOSEC can solve. And here, for the change and for the rewritten relaxed VQP, we have the number of the variables, the matrix side, and linear constant. And we can see that how the number of variables are bigger, and it grows to up to 1 million, more than 1 million. And also we have the linear constant, which is going to 500,000. So it's a very large problem. So for your question about the size of the matrices, yeah, here is our result that for this randomly generated VQP, and you can see the results of comparing Lorraine and MOSEC. And for Lorraine, we have the number of iterations, the CG iteration, and the CPU time. And for MOSEC, we have the CPU time. And I again said that this Lorraine is solving the larger problem, and MOSEC is solving the smaller problem. And still, we can see that MOSEC couldn't solve problems for VQP size more than 30 because of the lack of memory of the computer. But still, Lorraine is solving and it's faster, although that's larger. So, and in this last slide, which I think was very fast, I brought some figures to show this comparison. And in here, we can see this blue line is Lorraine, and this one is MOSEC, and we can see the figure of the MOSEC and Lorraine CPU time versus the number of the variables here. And we can see that we have this complexities here, and we can see that the green one in MOSEC, the exponent here is 2.15, but for Lorraine is 1.5, which shows that Lorraine is almost 1 magnitude faster than MOSEC. And also they have almost, MOSEC has almost a cubic complexity, but they have something between linear and quadratic complexity. And it shows that how it goes quickly to the number, the CPU time quickly goes to the number by the number of the variables. And by looking at this two and this two, we can see that still Lorraine could go farther before even reach that level of 10,000 for MOSEC here. And what else? And on the right hand side, you can see that the figure of the Lorraine CPU time per CG equation versus the number of the variables. And we can see that Lorraine has almost a linear complexity. Sorry if I was fast. Thank you very much for your attention.
Other questions?
So when you give the problem to MOSEC, you do moment variable substitution. For instance, you know, since you have xi square equal xi, a lot of variables in your moment formulation are actually can be discarded by.
Yeah.
Yes, yes. We are using block topology to generate.
Yeah.
So you showed us, you tested on randomly generated examples. We also like have a special set of particularly difficult BQPs.
I think definitely we have that reason we're trying it at least on the randomly generated problem. We believe that is enough to show that the thing that you're doing is good enough. But yeah, of course, there are a set of BQP problems, and maybe, yeah, please. Go ahead.
Yeah, maybe you can call this call problems. I was looking for problems.
Yeah.
But most of the difficult problems in the on the web are sparse problems with sparse matrices. We are looking for dense matrices. There are a couple of them which show like 3 or 4 problems which
So there's not a literature on like specially engineered BQPs to be difficult and dense.
No, I didn't find it.
So how do you know that ahead of time that this will have a low rank solution?
You mean by this order of the
So
relaxation?
you randomly generate an instance.
Yeah.
Right. So then how do you know that this instance is going to have a low rank?
So we solved one problem in one order of the relaxation, and we solved lots of them. But for example, considering the order of the relaxation to be 2. And we know that for these problems, which generated by in this way, we definitely get with the order of the relaxation, we will definitely get the low rank solution. So
right, I mean,
it's based on the experiment.
Is high enough that you get a low rank, you get a rank 1 solution, right? But presumably you don't go that high, or do you go that high?
No, we didn't go that high.
Actually, we can go that high, but these problems generated in this way, we never needed to go that high. Was always there was always a solution to that problem, and relaxation order 2 was always good.
But you couldn't go for all the ones back.
No.
I see. So you're saying that it didn't always happen that the low level of the hierarchy already gave you a solution for this sort of different problem. But I guess my question was sort of in principle, the algorithm assumption is that you have a low rank solution, right? So now I guess maybe in a way, if you find it, then you say, then the reason that it worked is because there was a low rank solution. It just kind of feels that things are a little bit, you first you say that there is a low rank solution. You assume for it to work, but then you just try it, and then if it works, then there was.
Well, there is a minor difference here. We don't assume exactness of the low rank solution. It doesn't have to be low rank. You don't assume it in the algorithm, you just assume it in the precondition. So if it's not low rank, it will just take more time.
I see. I see.
No. And why didn't you find this max cache? Because there were 2 spots.
Yeah, I think the problem was from the sparsity, but I didn't.
Function generate max problems, random max problems, and data.
Yeah, I didn't think about it. I don't know. You tell me.
I was looking at the black areas of the problems.
But
you can generate.
Go ahead. But why wouldn't it work also for class metric problem?
It would, but it would not be that efficient. I mean, the difference could be more significant. It would.
So will it work similarly if you have a feasible set which is not finite, or even if the optimal solution at the end is low?
So I don't know. I haven't thought about it, but I think it should work the same. I don't know.
In principle, it's just an integer concept, just like MOSEC. So the algorithm will work just as MOSEC. The only difference is in the efficiency.
So where was the particular structure of the Boolean cube exploited in your algorithm compared to if you were to use it on a different moment relaxation of a different problem?
Sorry, I missed one.
So where did you exploit the fact that your constraint is a Boolean cube rather than different constraints there?
Don't know if I get the question well, but yeah, I really don't know the answer. I don't know if I got the question, but
But I
Okay,
guess
fine.
it's so that the solution is too low and
Oh, but
yeah, maybe.
you would have it in other moment relaxation. Right? Maybe not at omega equals to 2, but eventually you would get lower.
But it's also in that assumption of the sparsity of that matrix D that you will get some favorable structures. So I like to explain.
Okay.
But why couldn't you develop a specific particle exploiting algorithm that would be similar to yours that would exploit this particle?
Yeah, I think we can do that in future, maybe.
Yeah.
Yeah, but you could beat the particle exploiting electration, but
Okay, this is one step.
More questions? We have a lot of time. Oh, one question in the chat.
So I can read it. Is the solver Lawrence available online?
Yeah, it is under, I think uploaded. I think it's in the
Not
poema.
really, it will be this.
All right, if there are no further questions, let's thank the speaker.